Okay, good morning. I hope you can hear me. You should be able to hear me now. If you can give me a thumbs up, that would be great. So I know the sound is working. Okay, excellent. Thank you. So we're going to finish up the course today with two more topics. So last time we covered time dilation. So the fact that times in a fixed reference frame, and a reference frame that is fixed to the points where the times are measured, fixed to the clocks. If the times are measured at the same time, those times, or the proper times, are the shortest possible time between events. And any time that is measured from a moving reference frame with respect to that reference frame will be measured to be larger. And that the factor by which it's larger is this gamma factor in special relativity, where gamma is 1 minus v squared. Oh, excuse me, I'm forgetting an important 1 over 1 minus v squared over c squared. So that's our gamma factor, and we also introduce beta as v over c, which is the fraction of the speed of light with which our object or our reference frames are moving. So that was time dilation. So time dilation, time as seen from a reference frame, a moving reference frame, where the time is measured at different points, measured at different positions, will be longer. Or in other words, time will if we use the time if we use the proper time as a fixed reference point, then time will be moving slower. So there's another result from special relativity, and remember, all of this came from the postulates from Einstein, which just said that the speed of light must be constant in any reference frame, and must be independent of the direction, and all of the physical laws are applicable in all inertial reference frames. So in addition to time dilation, we're also going to introduce now length contraction. So that's a very closely related phenomenon, which also follows from the same postulates, which will now say, or which will now state, that the length of an object as seen in a moving reference frame is shorter than the length of the object in its own rest frame. So length of an object as measured in a moving reference frame is longer than the length measured in the rest frame, where the rest frame is the frame of reference that doesn't move with respect to the object. So if we look at an example here, so we're going to go back to our muons, which we've used in the past lecture. So if we have a muon that in this case, for whatever reason, is going horizontal, most muons are actually going to go vertical, but the muon goes horizontal, and it is measured by the observer that's standing on Earth to travel for 2.1 kilometers. In the rest frame, or in the frame, sorry, this is the rest frame of this measurement, because the points are at a distance apart, and the observer is not moving with respect to the points where they're measuring the length from. They're not measured. The observer is in the same frame of reference as the length where these things where the events actually happen. In the rest frame of the muon, the observer is now moving at a velocity v, and it will appear to the muon that this distance is shorter. So we can actually calculate the distances here in both of those cases and derive the connection between the length as measured by the observer on Earth and the length as measured if the muon were something that could measure as seen by the muon. So let's start with the first part here. This is going to be the proper length. That's the length of this distance in the frame of reference of the observer on Earth, who does not move with respect to the points where these events are happening. So in this case, the length is just going to be the velocity with which the muon is moving times delta t, which is the time that the observer on Earth measures. So in the case of a muon traveling with velocity v, so then the length 0, which is the proper length, is the length measured by the observer on Earth, So that is going to be v times delta t, where delta t is the time measured by the observer between the two decays. The length measured by the muon is going to be, the muon thinks it's moving at a velocity v because it sees the observer fly by at the velocity v. So the muon still agrees with the observer on the velocities. That's one of the things that I didn't point out last time, but there's still symmetry in all of this, right? If the muon is moving with a velocity v in the direction to the right, that will still mean that the observer is moving with a velocity v in the opposite direction in the moving reference frame of the muon. So we still have all of our symmetry. That doesn't give a preference to one reference frame over another. So in this moving reference frame for the muon itself, the muon, so this is in the muon reference frame, the muon will measure a length that is v times delta tau. So the muon will think that it's going with a velocity v, so the length must be v times delta tau. So now we can of course calculate what L in the muon reference frame will be in terms of the proper length, the actual length that the muon traveled in a reference frame that doesn't move with respect to the points where those points were measured. So that will be v times delta tau. V is L0 over delta t, so that's L0 over delta t times delta tau. So that is going to be now, because delta t is equal to gamma delta tau, that will be L0 times 1 over gamma. Or in other words, it actually is L0 times 1 minus beta squared if we plug in the expression for gamma. So again, this is the length as seen in a moving reference frame, and then this length L0 is as measured in the object's rest frame. So again, we see that there's a change in the length of objects, just like there's a change in the time that is measured, depending on the speed of the reference frame with which you're measuring. So let's see, Isaac is asking, what's the word before length in the L0? Proper length, probably, right? So this is similar to proper time, which is the time as measured in a reference frame where the clocks aren't moving. Proper length is the reference frame, is the length as measured in a reference frame where the object isn't moving. So the reference frame, or the reference frame where the object, if you're measuring an object, in this case, of course, the object is in some sense, an imaginary ruler we would put here, and we would measure the length of that ruler. Obviously, the mu1 is traveling from one side of the ruler to the other side of the ruler, but the object in this situation that we're measuring is the length of the distance between those two points. Now, there is something to be careful about in length contraction, and that is that this only affects lengths as measured along the direction of motion. So if we had, a very fast skateboarder who's going close to the speed of light, who has a ruler that is 1 meter long, 1 meter stick, and this meter stick is moving or the length of that meter stick is moving in a direction, is pointing in a direction perpendicular to the velocity v. Now this, the person on the skateboard and the person who's observing and who's not moving, they'll agree on this length because it's perpendicular to the direction of motion. It's only in the direction of motion that the lengths will change. And so in fact, the person on the skateboard will see a length of a thickness of the ruler in the direction along the direction of motion that will be different. So in some sense, we have to keep those directions and those lengths carefully separate, that the change only happens in the direction along the direction of motion, or the effect of length contraction only happens in the direction along the direction of motion. The length in the perpendicular direction does not change. And so this actually, I'm putting this picture in here not necessarily for the problem itself, but this actually leads to some interesting effects, which you can sort of see the Earth shown here as as somewhat of a pancake instead of a sphere. So in the rest frame of the Earth, and in this case the closest star, the Earth has its proper length shape, and in that reference frame, the size of the Earth along the direction of motion is the same as the size of the Earth perpendicular to the direction of motion. Now, in a moving reference frame, when we have this astronaut that's moving very quickly, in this reference frame, this is not the proper length or the proper shape of the Earth anymore. What has happened is that the length along the direction of motion has contracted, but the length perpendicular to the direction of motion has not contracted. And so what happens is that the Earth actually starts to look thinner, and it starts to look like a pancake if you're moving with very high velocities. And so you'll see this in some Hollywood movies. They're using these kind of effects. They're exaggerating them, of course, quite a bit. And the other thing that we're talking about here is special relativity. Typically in Hollywood movies, and I'm thinking of Interstellar, for example. They're also using they're using general relativity. So they're using the effect of gravitation, which we're kind of ignoring here on all of this. This effect of the pancake shape of the Earth is actually very important in some of my own research, where we are colliding nuclei together. So if we have one nucleus coming in this direction, let's say we have a lead nucleus on a lead nucleus. So a lead nucleus at rest will look like this, will look spherical. But once we have two accelerated particle beams, the one lead nucleus that is coming from one direction will go with a very high velocity with respect to the rest frame of the other nucleus. So they're actually going to look like two pancakes that fly into each other, rather than two mostly spherical nuclei, which changes, of course, some of the expectations of what you expect to see. In particular, when these nuclei ultimately collide, the particles that are created in those collisions will have to go through a lot more nuclear material in this direction than if they're coming out in this direction. So you can actually observe that in experiments. So the difference in length of nuclear material through which the particles have to go. So in this case, the y component, if you wanna call this the y component, and this typically would call this the z component. This is the direction along which the velocity is, right? So this is the direction along which there has been contraction from the original spherical shape to the pancake shape, whereas in the y direction there's no change in this shape. Okay, so interesting effects happen in special relativity. There's a set of books by a physicist who was involved in the Manhattan Project back in the 50s, well, in the 40s, and then wrote the book in the 50s, which is the Wonderful World of Mr. Tompkins. And this is the premise of the book is that the speed of light is for some reason suddenly about the speed is reduced to about the speed of a car, and so it becomes very easy to reach speeds that are close to the speed of light, and so all of these effects are of course exaggerated, because in your daily life you've probably never really noticed any length contraction, and it would require very high velocities for you to be able to see that. Okay, so the last thing we're going to do in this course is tie this new approach of Lorentz of special relativity, tie this back to the original thing we started with, which was the transformations between coordinate systems in Newton's laws. So as you might remember, in Newton's laws, or in what we started with, oops, there we go, was what are called Galilean transformations. So those are the coordinate transformations we've used in this entire course up till now, and they say that x in a moving reference frame, if we have, so let me be explicit here. So this is a transformation from a reference frame S to a moving reference frame S prime, where S prime is going with a velocity v. So that's this S prime reference frame is going with a velocity v. So if something happens at a point x in the original reference frame, it will happen at point x prime in the new reference frame, and x will have to be equal to x prime plus v times t, right? And you know, I'm going to add, I added a prime here on the time, but of course t and t prime are the same in or traditional description of all of this. There's no different time in Galilean transformations. There's one time, and everyone in every reference frame agrees on that time. And then of course there's y is y prime and z is z prime. In those other coordinate directions, x in z and in y, there's of course no change in the coordinate. So this is the Galilean coordinate transformation to go from a fixed reference frame to a moving reference frame. And from that, everything else, of course, derives, right? We can calculate the first derivatives to the time of all of this. So we'll get ux is dx dt. That will be ux prime dx prime dt plus v. And so we actually get our relative velocity. So the velocity in the fixed reference frame will be the velocity of the reference frame itself, the moving reference frame, and then the velocity in that moving reference frame. In the time direction, of course, we can't take any derivatives to the time, or at least that'd be trivial. In the y direction, we have that the velocity components are unchanged, and the same thing in the z direction. And then we can take another derivative and get that ax is ax prime, ay is ay prime, and az is az prime. So also the accelerations are unchanged. And of course that allows us then to say that f is equal to ma is valid in all of those reference frames. Now we are going to have to change this, because we already realized that this is limiting if we want to write that the velocity or that the speed of light is constant, then that violates in particular this expression here. So if we have the fact that a speed of light or that the speeds are changed by just adding a velocity, that can't be true if, for example, ux is equal to c, then ux prime would be c plus v, which violates Einstein's postulate. So what we're going to do is we're going to imagine, so we're going to derive a new type of coordinate transformation, which is called the Lorentz transformation, which describes how to go from one reference frame to a moving reference frame, a reference frame that's moving with respect to the first reference frame, in a way that preserves the fact that the speed of light is constant. And so that will be interesting to see how we're going to do that. And actually, we're not going to derive it. I'm just going to give you the expressions, and then we're going to prove that they work. So let's imagine we have a pulse of light that starts at the origin. At the origin of reference frame S. So our fixed reference frame here, at the origin, there's a pulse of light that gets emitted. Now what will happen after a time t in the fixed reference frame, the pulse of light will have reached a distance of c times t. So after time t, the distance to the origin is going to be c times t. In deriving, so if we wanted to write this, of course we can write this in coordinates. So x squared plus y squared plus z squared minus c squared t squared is equal to 0, where this is the squared distance, and I've squared the distance to the origin there. Now this has to be true in all reference frames. So also x squared plus y squared plus z squared, x prime squared plus y prime squared plus z prime squared minus c squared t prime squared will have to be equal to 0 in the moving reference frame S. S prime, right? What we're assuming here is that at time t0, the reference frames have an origin that agrees with each other. And of course, that's similar to what we did here in the Galilean transformation. At time t equals 0, there's no distance, there's no difference between the two reference frames. So if that is true, there has to be a different transformation than the one we've written here for the Galilean transformation, because we can see that the Galilean transformation is not going to work because of that way the x component is transforming. Now it makes a little bit of sense now what is going to happen next. So we're going to introduce a new set of transformations. I'm going to start writing at the bottom here. So I'm going to start with z is going to be equal to z prime. We're going to assume that in the direction perpendicular to the motion, nothing is going to happen. Nothing different happens. And this relates, of course, to the fact that there's also no change in the length in anything perpendicular to the direction of motion. So we're going to assume that in the coordinate transformation, there's no change either. Y will therefore be equal to y prime. Now we're going to change x, which used to be x prime plus v times t prime. We're going to change that by multiplying with our relativistic gamma factor, which, this still looks fairly similar. And in particular for gamma, or for very small velocities beta of the reference frames, gamma will be approximately equal to 1. And so we have something that looks very similar to the original Galilean transformation. Now the one that looks quite different is going to be the transformation for the time. So that will be gamma times the time in the moving reference frame plus Vx prime over c squared. Now this is going to be the new term that you would not have expected there. So for beta approximately equal to 0, gamma is approximately equal to 1, and in this case, of course, v is much less than the speed of light. So if we use that, we find that x is approximately equal to x prime plus v times t prime. T is approximately equal to, let's look at what we have here in the expression. So gamma will be approximately 1, so we're just going to have t prime there. And then v is much less than c, and it's certainly going to be much less than c squared. So we're going to just ignore the second term, and then y is y prime, and z is c prime. So at very low velocities, we get something that looks like the original Galilean transformation. But this also satisfies the transformation, or this also satisfies this expression, or this it satisfies the second expression when the first one is satisfied and the other way around. So for our light pulse that starts at the origin, we can calculate what is x squared plus y squared plus v squared minus c squared t squared, and write it in terms of the primed variables. So if we write x squared plus y squared plus c squared minus c squared t squared, that will be equal to, if we just plug in the numbers now, so we're going to have our x component, that's going to be gamma squared x prime squared plus v squared t prime squared plus 2x prime v t prime. Then we have our y squared, which is actually going to be now y prime squared plus z prime squared. And then we have our time component. I'm going to start a new line here. So we're going to get minus c squared times the time squared. So that's going to have another gamma squared. And then t prime squared plus v squared over c to the fourth x prime squared plus 2t prime vx prime over c squared. Okay, so this looks a little bit complicated. If you look at the terms that we have here, you'll actually see that we have the cross terms with x prime and t each have a 2 times v times gamma squared prefactor. Here, our term with x prime and t has a 2 times v times gamma squared because the c squareds cancel out. And they're different in sign, so they're actually going to cancel out with respect to each other. So then the remaining terms, if we put all of the x components together, we'll have a gamma squared, and then we'll have an x prime component. Let's write x prime squared, and we'll have one from here, and we'll have another one from here, which will have a minus sign, and then a v squared over c squared. And we have our y prime squared, z prime squared, minus c squared. And now we're going to have a gamma squared 1 from this t prime squared. And then we have a c squared that we bring out the front. So we're going to have to divide this by c squared. So we get 1 minus v squared over c squared. And now, of course, you see what's happening. Gamma is equal to 1 over 1 minus v squared over c squared. So gamma squared is 1 over 1 minus v squared over c squared, and gamma squared times 1 minus v squared over c squared will be equal to 1. So this is equal to 1, and this is equal to 1. Oh, I missed my t prime squared here. So this is going to be x prime squared plus y prime squared plus c prime squared minus c squared t prime squared. So we actually have something that keeps this distance of the light pulse to the origin invariant. This coordinate transformation, or Lorentz transformation, has two properties. It reverts back to the Galilean transformation that we know and love from all of our slow velocity physics, all of the non-special relativity physics, and that worked for Newton, and it worked for obviously Galileo, since it's called the Galilean transformation. So it worked all the way through 1907 or whenever this special relativity transformation was written down. But it also has the benefit that it follows Einstein's postulates. In particular, it keeps the speed of light constant. No matter in which reference frame we measure the speed of light, we will get the same speed of light. And we've shown that it does that because of this expression, because it doesn't change or expression for the distance of the laser of the light pulse from the origin. And now, of course, we can go to the next step. It's a little bit more complicated in this case, but we can turn this into a transformation of velocities. So remember that in the case of the Galilean transformation, we just take the derivative d dt, right? And d dt is equal to d dt prime. Now that is something that we can't do anymore now. The changes from ddt, because of the time, ddt is not the same as ddt prime. So we're gonna have to do a little bit more work. So we're gonna be able to write first dx is equal to gamma dx prime plus v dt prime. Is gamma dx prime plus v dt prime. We'll be able to write dt is, and I'm just going to go to the dt term, and I'm not going to bother about the y and the z components for now. So we're going to get dt is gamma dt prime plus v dx prime over c squared, and then dx, dy and dz, right? So from that now we can calculate dx dt by dividing those two by each other, and we're going to find, so the gammas are of course going to cancel out, so we're going to get dx prime plus v dt prime over dt prime plus v dx prime over c squared. And if we divide the numerator and the denominator both by dt prime, we find dx prime dt prime plus v over 1 plus v over c squared dx prime dt prime. So what that indicates is that we have a conversion from our ux, that's the velocity that something has in the original fixed reference frame, to ux prime, which is the velocity that something has in the moving reference frame. And again, once if you plug in very small values of v compared to the speed of light, you'll see that this term is actually the thing that drops out, and for beta approximately equal to 0, this becomes ux prime plus v, which is again the thing we had already derived for the Galilean transformation. So the only thing that becomes different now is that this expression becomes a little bit more complicated. And one thing I've actually done unintentionally here is written this as a dot product, because ultimately the way this expression can be written down very summarized in very compactly is that the new speed will be in vector form. The old speed, or the speed in the non-moving reference frame, will be the speed in the moving reference frame, plus the speed plus the velocity of the reference frame over 1 plus v dot u prime over c squared. And so this is the relativistic transformation of velocities that derives from the Lorentz transformation itself. So yeah, you're asking why is this important for the final? So this particular thing is not as important for the final. I'm just saying this because this is going to be okay. And now 20 people dropped out of the stream right now. So this is not necessarily as important, but knowing that there is a coordinate transformation that transforms from one reference frame to another is something that is important. So we cannot use anymore or traditional Galilean transformation in high velocities. So this is a very fundamental thing about special relativity that we have to keep in mind. So in the formula we derived here, so just as a reminder, so this is the velocity of something in the fixed reference frame, in a fixed reference frame, and this is going to be u prime is going to be the velocity of that thing. I'm not going to write something again. Velocity in the moving reference frame, and then of course they're connected with v. That's the velocity of the reference frame. Okay, so that's all. That's all we really have time for. The rest of the chapter, in particular 5.7 and so on, relies on material that you haven't necessarily covered yet in this course. In particular, Doppler effect, which talks about waves and so on. So no need to read that. So this ends the material at 5.6. We're not going to do any problems, and again, 5.6 is not going to be a very important part of the exam. But it is, it is interesting mathematics. There's a lot more we could talk about here in terms of the mathematics that underlies these transformations, because it suddenly has changed the number of things we have to transform from 3, the positions x, y, and z, to x, y, z, and t. And suddenly this is where the expression that time is a fourth coordinate, of course, is coming from, because suddenly you can't treat time as being any more special, and it has to be treated at the same level as positional coordinates in some sense. And so if you go to a different reference frame, you're also going to a different reference frame for the times. Okay, so I'm gonna stop the recording here and then go back to Gathertown, since I see there might be some questions about the exam. So.